today's goal of this lecture. Today I will see some questions about homeomorphism. How many homeomorphisms exist from a group to another group? This is today's goal of this lecture. Okay? This topic actually very important for any competitive exam. But at first I will highly recommend you, if you don't see my previous video of group theory, please see at first my previous video of group theory. Because group theory, this part is actually very important for higher study. Okay? And today's part actually review part. For review, today I have discussed this part. Okay? So, let's see some question. How many homeomorphisms exist from a group to another group? Okay? Well. We all of us know the shortcut trick of counting process of homomorphism is, let G and G dash be two groups, then following step can be used to find number of homomorphism from G to G dash. First, find all normal subgroup of G. This is the first step. Step 1. Choose any normal subgroup S and construct G mod S. Say G mod S equal to K. Step 2. Find the number of subgroup in G dash that are isomorphic to K. That means we have to find number of subgroup of order K in G dash. Consider this is N1. Then we have to find order of automorphism of K. Say this is N2. Then the number of homomorphism would be N times automorphism. Consider this is not N, N1 times automorphism of K. This is the shortcut trick to find the counting homomorphism from any group to another group. We all of us know, in my previous video I have defined this type of question actually briefly. For example, see how many homomorphism means number of homomorphism from the group Z to S3. Z to S3, how many homomorphism exist? And there exists one shortcut trick, short trick. And trick is number of homomorphism from any infinite cyclic group to Sn are actually n factorial. That means this would be, since this is the infinite group, this would be 3 factorial, means 3 into 2, 6. Now I will apply this method. We all of us know the normal subgroup of Z are look like Z, 2Z, 3Z, 4Z, 5Z, so on. And number of subgroup in S3 are look like, number of subgroup in S3, one S3, another trivial subgroup, and subgroup of order 2 is identity 1, 2, identity 1, 3, identity 2, 3. And subgroup of order 3 is identity 1, 2, 3, 1, 3, 2. This is the number of subgroup in Z3. This is number of two subgroup order, the subgroup of order 2 in S3, and this is the subgroup of order 3 in S3. If we consider Z mod Z, then this is isomorphic to identity, and which is subgroup, obviously this is subgroup of S3, and automorphism of identity means actually Z1. Automorphism of Z1 is 1, and number of subgroup in 1 in Z1 is only 1, that means this would be 1. Next, if we consider normal subgroup 2Z, then Z mod 2Z would be isomorphic to Z2. And in S3, there are 3 subgroup of order T, 2. and automorphism of Z2 is actually phi 2 and phi 2 equal to 1, and there are 3 subgroup of order 2, so this is 3, so this would be 3. The mapping would be such type 2Z map to identity and 1 plus 2Z. This is either it map to 1 2 or 1 3 or 2 3. There are 3 choices. This is the picture. This would be image for this homeomorphism. Next, another possibility is Z mod 3Z, and Z mod 3Z is isomorphic to Z3, and automorphism of Z3 is phi 3 and phi 3 equal to 2, and there are 1 subgroup of order 3 in S3. So this would be 1, 2 times 1, this would be 1. And for this mapping, the mapping would be such type 3Z map to identity, since this is the normal subgroup. 1 plus 3Z would be map to either 1 2 3 or 1 3 2. That means there are 2 choices. Number of choices is 2, and 2 plus 3Z. If this map to 1 2 3, then 2 plus 3Z would be map to 1 3 2. If this map 1 plus 3Z map to 1 3 2, then this would be map to 2 plus 3Z map to 1 2 3. That means there are 1 choices. So number of choices is here 2. So number of homeomorphism from Z to S3 1 plus 3 plus 2, this would be 6. And the shortcut trick is n factorial, which is equal to 3 factorial means 6. I hope my all viewers have understood this is clearly. Okay, well. Now I will see counting homomorphism from the function S5 to Z10. We all of us know this rule, shortcut tricks. In my previous video I had seen, I have given the link in the playlist Sn to Zm. When m is odd, then number of homomorphism is 1, and if m is even, then number of homomorphism is 2. So this is the shortcut trick we all of us know. Why this would be, since here m is even, so this would be 2, because here the normal subgroup is identity in S5, identity A5 and S5. S5 modulo identity, these would be isomorphic to S5, and this is not be subgroup of Z10. S5 modulo A5, this is isomorphic to Z2, and Z2 is a subgroup of Z10. S5 modulo S5, this is isomorphic to Z1, which is subgroup of Z10. And for this automorphism of Z2 is 1, and we all of us know in Z10 there exists one subgroup of order 2. So this would be 1 times 1, this would be 1. Here for Z1, this is actually the trivial homomorphism. So there exists 2 type of homomorphism. One for this normal subgroup A5, and when the normal subgroup is S5, this is actually trivial homomorphism. So number of homomorphism is 2. Now I will see the number of homomorphism from A4 to Z6. The shortcut trait A4 to Zm is 3 when 3 divide m and 1 when 3 does not divide m. Notice in A4 there are normal subgroup are identity K4 and A4. Then A4 modulo identity, this is actually isomorphic to A4, and A4 does not be subgroup of Z6. A4 modulo K4, this is isomorphic to Z3, and Z3 is a subgroup of Z6. A4 modulo A4, this is actually the trivial homomorphism which is subgroup of Z6, and here automorphism of Z3 is equal to 2. So number of homomorphism is 2 plus 1 equal to 3. But if the question is A4 to Z5, then always would be 1, because 3 does not divide m. Now I will say the number of homomorphism from n to Zm when n greater than equal to 5. This is actually trivial homomorphism, because if we consider the homomorphism A from A6 to Z10 when n greater than equal to 5, since an when n greater than equal to 5, this is actually simple group, that means only normal subgroup is identity and A6, then A4 modulo identity, this is actually isomorphic to A4 and this is not be subgroup of Z10, and A4 modulo A4, this is actually isomorphic to Z1 and Z1 is subgroup of Z10. So only trivial homomorphism possible. So when n greater than equal to 5, then an to Zm, since the an group is simple for n greater than equal to 5, so only there exists trivial homomorphism. Now I will say one new type of homeomorphism. Find the homeomorphism, all homeomorphism from Q with Q star non-zero rational number with multiplication to integer with addition. Consider for this phi b homomorphism such that phi of 1 equal to 0 and phi of minus 1. How would be phi of minus 1? We can write this as phi of 1, we can write this as phi of minus 1 times minus 1, and by the property of homomorphism, this is equal to phi of minus 1 plus phi of minus 1, and this is equal to 2 phi of minus 1. And notice here I have got phi of 1 equal to 0. So that implies phi of minus 1 equal to 0. Therefore, the homomorphism is look like phi of 1 equal to 0 and phi of minus 1 equal to 0. And here the homeomorphism from non-zero rational number to integer with respect to addition, here non-zero rational number with multiplication. Consider in Q the pointer look like A by B. consider A over B equal to, we can write this as P1 alpha 1, P2 alpha 2 up to Pk alpha k times Q1 beta 1, sorry, Q1 minus beta 1, B, we can write B as Q2 minus beta 2 up to Qk minus beta k, where these P1, P2, Pk are prime number and also Q1, Q2, Qk are prime number. Okay, so we can write AB such as P1 alpha 1, P2 alpha 2 up to Pk alpha k, where these alpha 1, alpha 2 up to alpha k belongs to integer. It may be negative or it may be positive. Therefore, phi of A over B equal to phi of P1 alpha 1, P2 alpha 2 up to Pk alpha k, and this is equal to, by the property of homeomorphism, since Q star to J star, so by the property of homeomorphism, this is equal to phi of P1 alpha 1 plus phi of P2 alpha 2 up to phi of Pk alpha k, Pk alpha k, where P be a prime number. Now my question, if there exists a function phi from P to Z, how look like the function? The function would be f of P equal to 2P. We can construct the function such as f of P equal to 2P. Therefore, phi of P1 alpha 1 plus phi of P2 alpha 2 Pk alpha k, we can write this as phi of P1 alpha 1 means this is equal to phi of P1 up to P1, this is alpha times, and since this is alpha times, so we can write this as alpha 1 times phi of P1, and since the function, we can construct a function f of P equal to 2P, so this is equal to 2 alpha 1 P1. Therefore, this is equal to 2 alpha 1 P1 plus 2 alpha 2 P2 up to 2 alpha k Pk. Therefore, phi of A over B equal to this. We can construct one function such type. Now, is it homomorphism? Because if you consider another element C over D would be such type Q1 alpha 1, Q2 alpha 2 up to Qk, Q1, here I have considered alpha 1, so here would be B1, B2 up to Qk beta k, Bk. Then phi of A over B times C over D, we can write this as phi of A over B plus phi of C over D. So obviously this is homeomorphism. And how many homeomorphisms exist? Infinitely many. Since here the function is phi from q with multiplication to z with addition, so here the homeomorphism would be such type 2 to the power alic naught, and which is c. That means there exist uncountable homeomorphism exist. I hope my all viewers have understood this is. Today I will stop here. In my next video I will discuss number of 1112 homomorphism. How many 1112 homomorphism exist from a group to another group? Okay, this is my next topic. In my next video I will discuss this topic. But at first I will highly recommend you please see today's video with pay attention. Because this part actually very important for any competitive exam. And if you have any queries from this question, let me know in the next class. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.